Hi everyone, my name is Sichao. I'm the technical marketing of Infineon Easy Power Modules. Today, I'm honored to introduce you about our 2 kV silicon carbide MOSFET leading edge technology and its product. As we have seen in the market, quite a few applications are or tend to moving to a higher DC link voltage up to 1500 volts. With 1200 volt devices, a lot of devices are needed to support a 1500 volt DC voltage. As a dual boost topology seen here from solar application. So here, either with IGBT or silicon carbide MOSFET or other complicated multi-level solutions like fly cap topologies. And in case of the DC-DC stage in charging, here's not really a visible silicon solution at all. And already a 1200 volt silicon carbide MOSFET based solution gets complicated in terms of device numbers. Now, the availability of low dynamic losses silicon carbide devices in a 2 kV classes, MOSFET and diodes make it possible to increase the power with half of the used device than before. With our 2 kV silicon carbide MOSFET, we have designed a technology with both low radiation times area and low cosmic ray induced fit rate at the same time. This makes the switch the perfect choice of your application with 1500 volt voltage. Besides the low fit rate, it is also extremely important to offer stability and blocking voltage over entire lifetime. We also have done tremendous number of qualification tests in order to guarantee that. The good news is that all our base technology have passed all the relevant tests already. With our latest innovation in gate structure, the so-called M1H technology, our 2 kV SiC MOSFET will still offer you full freedom in choosing turn-off gate voltage. This will make your design much easier. Last but not least, we equipped for our discrete portfolio, specially designed DO packages with higher creepage and clearance distance than standard discrete, so that you can fully utilize the higher blocking voltage in your application. And now let's look at the radiation and cosmic ray induced fit rate first. So in the left side of the slides, we have plotted the comparison of radiation times area and the maximum drain source voltage in different silicon carbide MOSFET technologies you could find on the market. The x-axis represents the maximum drain source voltage, and the y-axis represents the radiation times area value. We have selected three 1.7 kV silicon carbide MOSFET technology from competitors and compared them to our 2 kV MOSFET. As you can see, our 2 kV SiC MOSFET offers you both higher blocking voltage and lower radiation at the same time. This is going to give you the ultimate performance with lots of design freedom at the same time. On the other hand, I would like to also draw your attention to the so-called cosmic ray induced failure rate. As you might know, power devices could randomly fail due to cosmic ray from the universe. This failure rate is dependent on many parameters, such as the device design itself, the applied voltage, the temperature, altitude, and so on. We at Infineon perform special tests to verify the fit rate of each technology against design values, and its results of our 2 kV silicon carbide MOSFET is plotted on the right side of the slides. Here, the x-axis represents the applied test voltage to the device, and the y-axis represents the failure rate, where we have to hidden to the exact value due to the know-how protection. For comparison purpose, we also plotted our 1.7 kV technology in the same diagram. As you can see, the extra blocking voltage can reduce the cosmic ray induced failure by around 1 magnitude. This parameter will become significant when you have large number of devices or your design application is at high altitude location. In such cases, thanks to the extra blocking voltage, your application will become more robust and reliable compared to using the 1.7 kV technology. And not only the blocking voltage of the device, but also the long-term stability of it is extremely important for your application. Here, the right combination of edge termination design and the choice of housing material makes the difference. With our over decades experience in designing and manufacturing silicon carbide device, we know how to design a robust product, even under harsh environmental conditions. For this purpose, we have performed many qualification tests to guarantee long-term stability of blocking voltage. In this slide, you can see selection of such tests. I would like to first draw your attention to the HTRB. So here, shown on top for this test, we have chosen the test voltage at associated voltage level of 2 kV, which is exactly 1.8 kV. Just for the record, this is already 100 volts more than the competitor's absolute blocking voltage. Our device has already passed this test. Next, I would also draw your attention to the last two tests at the bottom. These are tests where high humidity level is present. We know today that many applications are installed outdoor without any protections. This leads to exposure of semiconductor devices inside it to a high humidity condition. To verify the stability of our 2 kV technology under such condition, we have performed two extended qualification tests, which is the first HV, H3TRB test, and the second, the dynamic H3TRB. In these two tests, we tested the device at increased humidity level, and thanks to our experience and knowledge, we can proudly say that our technology can already pass such challenging tests. This should give your application an extra boost in robustness and reliability. And in addition to a 2 kV voltage class, the latest base technology advancements regarding gate voltage operation are also implemented. This news you can also find in our new 1200 volt silicon carbide MOSFET product currently, which is in rollout. And in this slide, you can see, so the maximum transient turn-off gate voltage is no longer limited for certain switching frequency range, while minus 10 volt is possible, independent of the switching frequency. This really enlarged operation range makes the design work easier as it is more robust against different gate driver circuitry designs. And the trade-off between overvoltages and the power losses efficiency is easier to manage. And in this slide, I would like to give you a guidance on designing the creepage and clearance when using a 2 kV MOSFET. The standard procedure of determining creepage and clearance is to look into the standard IEC 60664-1 and look after distance value by given voltage in your application. However, you might have to consider an extension of the standard, which is IEC 60664-4, once the switching frequency in your application is higher than 30 kilohertz. And why is that? So please look at the left side. You can see tests we have conducted in our lab on a standard TO247 housing with a switching frequency at 80 kilohertz. The 2.6 millimeter clearance fulfills requirement from the 60664-1. However, due to the inhomogeneous field at such high frequency, you still look at plasma caused by ionization of air. This effect is called as corona high frequency discharge and must be eliminated in application. And the extended standard, the IEC 60664-4, provides a guidance on how to avoid such effect by enlarging clearance distance. And this is shown on the right picture. So the x-axis is the peak value of the repetitive voltage in your application, and the y-axis is then the minimum clearance required. You will also find two curves here. So the gray curve represents the standard device distance you will find from the IEC 60664-1, and the orange one is the value you find from the IEC 60664-4, considering the frequency more than 30 kilohertz. You can immediately see the requirement of higher clearance is getting more obvious with the peak voltage getting higher. For example, with the peak voltage at 2 kV, you are looking at a factor of 11 between both lines. But the good news is that our packages, both in discrete and the module, are already made for such high requirements. You also have to consider this in your system design, nevertheless. So talking about product, we will first bring out this 2 kV silicon carbide MOSFET technology in two housings, the 62 millimeters and the EZ3B packages. With 62 millimeter, you are looking at a standard half bridge configuration, and the RDS range from 6 milliohm down to 3 milliohm. Our primary target application are auxiliary power supply for traction, the EV charging, the energy storage, and also the solid-state circuit breaker. Samples are available now. The start of production is planned in next month. With EZ3B on the right side, we are bringing out a product specially designed for a 1500-volt PV application. This product comes with a 4-channel boost setup, which could work as an MPPT stage in a 1500-volt PV string inverter. Each channel features a 19 milliohm RDS MOSFET and paired with a 40 amps 2 kV silicon carbide diode, which we also developed specially for this purpose. The product is going to offer you a simple but reliable and high power density solution for your 1500-volt high power PV string inverter. And together with our another product, EZ4B, which we have also already launched, you can easily make a PV inverter to an output power over 300 kilowatts. And also for discrete, in the new TO247 package, the MOSFET will be rolled out in 5 RDS ratings, so start from 12 milliohm up to 100 milliohm. These types are matched by also matching diodes ampere rating from 80 amps down to 10 amps. Samples are available now for the MOSFET and will be available soon for the diodes. Thank you for your attention. I'm looking forward to hear the feedback and having the discussion with you about these exciting technologies.